Welcome to Secrets of History at Night. We journey into the past to help you drift off to peaceful slumber. Don't forget to subscribe and hit that like button, because by the time this lecture concludes, you'll be fast asleep. Close your eyes. The story is about to unfold. Amidst the countless stars scattered across the vast expanse of the cosmos, myriad planets revolve. Many of these celestial bodies may harbor extraterrestrial life. Some worlds are submerged in endless oceans, their depths potentially concealing organisms unlike any terrestrial forms. Others beneath icy crusts safeguard dark waters where minuscule beings sustained by subterranean chemistry might exist. There are planets astonishingly similar to Earth, bathed in the gentle glow of their star, adorned with delicate clouds, and possessing conditions that hint at the possibility of advanced alien civilizations. Probes traverse the solar system's expanses. Telescopes capture the light of distant worlds. Each particle of data ignites hope for a discovery that could redefine everything. For centuries, humanity has striven to understand if we are alone in the galaxy. Astronomers scan the stars to locate new planets, while engineers construct craft designed to touch the soil of other worlds. Writers craft tales of encounters with unknown beings, and researchers analyze molecules captured in space. A radio wave, a trace of gas, or a speck of organic material. Any hint sparks curiosity. The universe remains silent, yet this quietude compels us to create new instruments to decipher its signals. The search for life extends across numerous horizons. Mars, scarred by craters and canyons, holds vestiges of conditions that, billions of years ago, could have sustained living organisms. The moons of Jupiter and Saturn, enshrouded in ice, conceal oceans where primordial life forms, fueled by the planet's internal energy, might reside. Planets orbiting distant stars, discovered in recent decades, bear a striking resemblance to Earth, and their atmospheres may contain gases indicative of life's potential. Our investigations encompass not only bacteria capable of thriving in harsh environments, but also civilizations that might transmit signals across galactic distances. Life, from a scientific perspective, is a series of chemical processes that evolve, adapt, and pass their traits to subsequent generations. This concept opens avenues for speculation. Life could exist in sub-ice seas where minerals and geothermal heat drive chemical reactions. It might inhabit methane oceans, where conditions differ fundamentally from those on Earth. Or perhaps it flourishes in the clouds of planets with extreme chemistries, governed by different laws. Each hypothesis adds vibrant hues to our cosmic panorama. Diverse approaches help us inch closer to unlocking this grand mystery. Rovers on Mars meticulously collect samples that could reveal the planet's past, when its climate was more temperate. Probes explore moons, whose depths tantalize with hints of biology. Telescopes like the James Webb meticulously capture the light of faraway worlds, seeking atmospheric gases associated with life. Methane detected in the Martian atmosphere, organic molecules emanating from moon geysers, and water vapor in exoplanet atmospheres. Each discovery, like a piece of a complex puzzle, expands our understanding of the cosmos. This quest intertwines the precision of measurements with the audacious curiosity that fuels discovery. Now, let us consider the conditions that foster life among the stars. Before embarking on our cosmic odyssey in pursuit of life, let us first ascertain the prerequisites for its emergence and evolution. For a considerable time, science posited that life could only arise where suitable chemical components and favorable external conditions were present. Today, we recognize life's remarkable adaptability and diversity. Yet three fundamental criteria consistently capture the attention of scientists. The first indispensable element is liquid water. Its significance stems from its unique physical and chemical properties. Water possesses the capacity to dissolve an extensive array of substances, facilitating the interaction of diverse chemical elements and compounds. Furthermore, water serves as a medium where molecules can readily move and interact with one another. Without this capacity for material and energetic exchange, the genesis and development of living organisms would be unimaginable. On Earth, liquid water covers a substantial portion of the planet and is the principal enabler of its biosphere's flourishing. Water can also exist under different conditions, such as beneath layers of ice or deep within the crusts of planets and moons. However, liquid water is generally considered the most promising medium for life's inception and sustenance. The second crucial component is carbon. Carbon is unparalleled in its chemical reactivity. Its atoms readily bond with each other, forming lengthy and stable chains or rings that serve as the backbone of complex organic molecules. These compounds are the fundamental building blocks of living cells, allowing for the formation of an immense variety of molecular structures essential for information storage, metabolic processes, and intricate biochemical functions. Carbon, indeed, is the optimal element for constructing a robust, advanced, and diverse biology, akin to that found on Earth. The third essential for life is energy. Without a continuous influx of energy, any living system cannot sustain its metabolic processes, growth, and reproduction. On Earth, our primary energy source is the sun, with plants capturing sunlight and converting it into chemical energy that fuels other organisms. Yet, life can persist even in the complete absence of sunlight, deriving energy through alternative means. A striking example of such conditions on our planet is found in deep-sea hydrothermal vents, known as black smokers. These are located at great ocean depths, where sunlight never penetrates. Here, superheated, mineral-rich fluids erupt from the Earth's interior under immense pressure. Entire ecosystems thrive around these underwater sources, where bacteria obtain energy not from the sun, but from chemical reactions, such as the oxidation of hydrogen sulfide and other compounds. These bacteria then become sustenance for more complex organisms, including worms, mollusks, crabs, and even deep sea fish. However, even when all three elements, water, carbon, and energy, are present, another vital condition comes into play: the habitable zone. This is the region surrounding a star where temperatures are sufficiently moderate to allow liquid water to exist on a planet's surface. It is sometimes referred to as the Goldilocks zone, analogous to the fairy tale where the protagonist chooses porridge that is neither too hot nor too cold, but just right. Our own planet is situated precisely in the middle of such a zone, at a distance of 1 astronomical unit from the Sun. It is thanks to this positioning that Earth enjoys a temperate climate and vast oceans, creating conditions conducive to life's proliferation. The boundaries of the habitable zone are influenced by the type of star, its temperature, and its size. For instance, smaller red dwarf stars have their habitable zones, much closer than hotter blue giants, where this region is situated significantly farther away. An illustration of the habitable zone's importance is Mars, which currently resides at its outer edge, having lost most of its surface water. Though conditions there may once have been far more favorable, it is also worth noting that life can evolve even in extremely adverse environments, such as areas of high radiation, boiling geyser waters, acidic lakes, and the complete darkness of deep caves. On Earth, such organisms are termed extremophiles, serving as testament to life's astonishing capacity to adapt to virtually any conditions nature presents. It is precisely these extremophiles that inspire scientists to seek life in the most unusual and challenging corners of the cosmos. To effectively conduct the search for life throughout the universe, astronomers have devised specialized systems to assess a planet's potential for fostering and sustaining life. Currently, 2 such index systems are actively employed, allowing for the evaluation of planetary prospects and the identification of the most intriguing worlds among numerous candidates for detailed study. The first system is known as the Earth Similarity Index, or ESI. This index takes into account 3 primary planetary parameters: mass, radius, and surface temperature. The assessment is provided on a scale from 0 to 1, with Earth serving as the benchmark, assigned the maximum value of 1. The closer a planet's score is to 1, the more its parameters resemble Earth's, thus increasing the likelihood that it might be suitable for life as we know it on our planet. A planet's mass is paramount, as it dictates the strength of its gravitational pull. Excessive gravity can lead a planet to retain a dense and heavy atmosphere, creating conditions challenging for life's development. Conversely, insufficient mass causes a planet to rapidly lose its atmosphere, also complicating the maintenance of stable surface conditions. A planet's radius influences its internal structure and the composition of its core. This, in turn, affects numerous crucial processes, including plate tectonics and the magnetic field, which shields the surface from radiation. Surface temperature, however, is a key determinant for the presence of liquid water and the viability of biochemical reactions, which underpin all known forms of life. Planets scoring high on the Earth. Similarity index typically 0.8 and above immediately capture the attention of astronomers. This indicates that conditions on these worlds closely mirror those on Earth, thereby enhancing the probability of life's existence there. Such planets may possess oceans, moderate temperatures, and an atmosphere comparable to Earth's, making them primary targets in many scientific missions. However, it would be a mistake to limit our search to exact replicas of Earth, given that nature can conjure entirely different forms of life in unexpected circumstances. Another system, the Planetary Habitability Index, or PHI, has been developed to broaden research horizons. Unlike the first index, PHI considers the potential for life based not only on familiar conditions, but also on entirely different chemical foundations. This approach enables scientists to hypothesize the existence of organisms on worlds that, at first glance, appear exceedingly inhospitable. The Planetary Habitability Index accounts for potential life forms that might utilize alternative chemical compounds and habitats. For instance, it considers conditions where other liquids, such as methane, ammonia, or hydrogen sulfide, play a pivotal role instead of water. While such environments are unsuitable for Earth-like life, they could quite possibly sustain entirely different, hypothetical types of organisms. Furthermore, the index incorporates the diversity of potential energy sources that could fuel biological processes. These might include not only sunlight, but also chemical energy derived from reactions between various substances in the atmosphere or within planetary interiors. Moreover, this assessment system even accounts for potential differences in the biochemistry of organisms themselves, which might not utilize carbon as their primary structural unit. The synergistic use of both indices creates a maximally comprehensive and flexible assessment system, empowering researchers to identify and prioritize not only worlds closely resembling Earth, but also planets that significantly deviate from our familiar conditions, yet still possess the potential for life's emergence and evolution. This integrated approach substantially increases the chances of making significant scientific breakthroughs and advancing our understanding of how diverse life can be throughout the universe. Until recently, scientists believed that life could only thrive under conditions mirroring those on Earth, with moderate temperatures, liquid water, and limited radiation. However, research conducted in recent decades has substantially expanded our comprehension of where life might exist. Organisms have been discovered on Earth capable of surviving in conditions previously deemed entirely unsuitable for any life forms. These discoveries have given rise to alternative hypotheses, suggesting that life in the universe might be far more varied than we previously imagined. One of the most intriguing hypotheses is the concept of life existing in methane seas. Although methane is an unsuitable solvent and even a toxic substance for terrestrial organisms, it can effectively function as water under different circumstances. At the low temperatures found on some celestial bodies, methane becomes a liquid, forming lakes and seas. Organisms with fundamentally different biochemistry could potentially evolve within these methane bodies. They could utilize compounds dissolved in liquid methane, much like earthbound organisms utilize solutes in water. A prime example of such conditions is found on Saturn's moon Titan. Its surface features large lakes and seas composed of liquid methane and ethane, regularly replenished by methane rains. In such an environment, hypothetical life could employ methane not only as a solvent, but also as the basis for its metabolism, forming a completely new and, as yet, unknown biochemical structure. Another fascinating hypothesis considers silicon as a potential alternative to carbon in the construction of organic life. Carbon is the unique element forming the basis of life on Earth. Owing to its ability to create long, stable chains and a variety of complex structures, silicon, being carbon's closest chemical analog, could theoretically also form chain-like structures and compounds that might serve as precursors for organic molecule analogs. However, silicon is more chemically reactive and tends to form solid, insoluble compounds like quartz and other minerals. Despite these limitations, under conditions of high temperature or a vastly different chemical environment, such as on hot planets with volcanic activity, silicon-based life might theoretically find a way to exist. Although this remains a purely hypothetical scenario to date, scientists seriously consider it as a potential avenue for the search for life in the extreme conditions of other planets. Yet another significant hypothesis explores the possibility of life existing under conditions of extremely high radiation. On Earth, radiation is considered a major limiting factor for organism survival. But certain bacteria and archaea exhibit remarkable resilience to radiation exposure. For instance, the bacterium Deinococcus radiodurans can withstand radiation doses thousands of times higher than the lethal level for humans. Organisms adapted to such harsh conditions might also exist in outer space, on the surfaces of planets with very thin atmospheres, or on the moons of gas giants, where radiation levels are significantly higher than on Earth. These organisms protect their DNA from damage through unique genetic repair mechanisms. These traits could also be characteristic of extraterrestrial life forms. Another alternative scenario involves life in hypersaline environments. On Earth, we already have examples of this. For instance, microorganisms inhabiting the Dead Sea or the hypersaline lakes of Antarctica thrive in high salt concentrations, which would be fatal to most conventional organisms. These bacteria and archaea are known as halophiles and are not only capable of tolerating extreme salinity, but also actively utilize it for energy acquisition. They possess specialized mechanisms that enable them to maintain fluid balance within their cells and survive at salt concentrations several times higher than those found in oceans. Similar conditions could arise on other planets and moons where water, due to specific environmental factors, has become highly saline. Earth organisms capable of surviving in these extreme conditions are collectively termed extremophiles. They have become perfectly adapted to the harsh environments of our planet and serve as models for understanding what life beyond Earth might be like. For example, microbes discovered in volcanic vents or hot springs suggest the possibility of life existing in similar conditions on other planets with significant volcanic activity. Microorganisms living beneath the Antarctic ice demonstrate how life can persist in the icy oceans of gas giant moons. Furthermore, Earth is known to harbor organisms capable of thriving in both extremely acidic and alkaline conditions. For instance, bacteria residing in the acidic lakes of volcanic craters can survive in environments with acidity levels comparable to concentrated sulfuric acid. Other microorganisms flourish in alkaline environments, such as hot springs rich in carbonates. These adaptations illustrate life's capacity to effectively utilize virtually any conditions nature provides, as long as a stable energy source and suitable chemical compounds are available. Thus, through Earth's extremophiles, we understand that life in the universe can manifest in the most improbable forms, employing entirely different mechanisms for survival and growth. Such examples significantly broaden the scope of the search for life, prompting astronomers and astrobiologists to investigate even the most peculiar corners of our universe. Having explored the fundamental conditions necessary for life's existence, it is appropriate to turn our attention to the worlds closest to us, the planets within our solar system. These have become the initial candidates for study, as they are accessible via robotic spacecraft and, potentially in the future, crewed missions. Among these celestial bodies, Mars stands out prominently, a planet that has captivated scientific and public interest for over a century. Fascination with Mars predates the advent of space probes. As early as ancient times, astronomers observed this bright reddish planet. However, the scientific study of Mars commenced much later, during the era of telescopic observation, beginning in the 15th century. Attention to Mars particularly intensified in the 19th century, as optical telescopes reached a level of sophistication, allowing for the discernment of contrasting dark and light regions on its surface. A pivotal moment was the Great Opposition of Mars in 1877. This astronomical event occurs roughly every 15 years, when Mars and Earth achieve their closest approach, aligning on the same side of the Sun. During these periods, the red planet is exceptionally bright, and details of its surface are observed with remarkable clarity. It was precisely during one such opposition that Italian astronomer Giovanni Schiaparelli compiled a detailed map of the Martian surface. He noted the presence of long, thin lines, which he termed canali, meaning channels or grooves. The translation of this term into English as canals ignited considerable excitement within scientific and public spheres, particularly in the English-speaking world. Canals began to be perceived not as natural formations, but as artificial constructs engineered by intelligent civilizations. Public imagination conjured visions of beings on Mars, striving to save their planet from drought, engineering a network of waterways from the poles to the equator. These ideas were particularly championed by American astronomer Percival Lowell, who dedicated several books and decades of observation to Mars. He claimed to see a complex system of intersecting lines, regular and symmetrical, interpreting it as evidence of advanced intelligence on the planet. He also established a dedicated observatory in Arizona for the study of the red planet. Although it later became evident that the canals were an optical illusion, stemming from the imperfections of early telescopes and the nuances of human visual perception of fine details. Despite the persistent notion of a human presence on Mars, the idea has significantly influenced our culture and ignited scientific curiosity. The dawn of the space age granted humanity the capability to transition from mere conjecture to genuine exploration. In the 1970s, American automated probes, Viking, were dispatched to Mars. Each mission comprised an orbiter and a lander, which achieved the first successful soft touchdown on the Martian surface and conducted a series of chemical analyses on the regolith. The onboard instrumentation was designed to detect organic compounds and any potential biological signatures. Although the outcomes did not conclusively confirm the existence of life, they marked a crucial phase in planetary investigation, enabling the first close-up assessment of its physical and chemical characteristics. In the subsequent decades, Mars became the focus of numerous missions. Orbiters provided high-resolution imagery of the terrain, revealing extensive geological formations, while rovers commenced direct on-site investigations. By the early 2000s, it was evident that numerous indicators of past water activity were present on the Martian surface. Ancient riverbeds, deltas, dried lake beds, and lacustrine deposits all suggest that the planet's climate was considerably milder and more humid billions of years ago. Rocks containing clay minerals exclusively form in the presence of water. Therefore, its past existence is undeniable. Furthermore, it was discovered that vast reserves of water ice are contained within the polar and near-surface layers. Ice is also detected in craters and beneath thin layers of dust, particularly in temperate latitudes. Of particular interest are the seasonal phenomena observed on the planet's surface. During warmer periods of the Martian year, dark streaks appear on crater slopes. These have been termed recurring slope lineae. They consistently appear in the same locations and vanish as temperatures decline. Initially, scientists hypothesized that these might be caused by the seepage of briny liquid water, especially given their seasonal nature. However, subsequent research indicated that temperatures in these areas remain too low for liquid water to exist stably. Currently, the most plausible explanation involves the movement of dry flows, dust, and sand particles, possibly across surfaces covered with salt deposits. Nevertheless, the precise nature of these processes remains an open question. The detection of methane plumes, registered by both orbital instruments and surface measurements, also warrants significant attention. Methane concentrations fluctuate throughout the year, increasing in summer and decreasing in winter. This seasonality is of heightened interest because, on Earth, a substantial portion of methane is produced by microbial activity. Geological processes, such as the chemical interaction of water with specific rock types, which can also release methane, are being considered as alternatives. Scenarios where the gas accumulates in subsurface cavities and periodically escapes through crustal fractures are also being discussed. The specific mechanism has yet to be definitively established, and the origin of Martian methane continues to be an active area of research. As data accumulates, it becomes increasingly apparent that Mars in its distant past possessed a vastly different climate. Current models suggest that approximately 4 billion years ago, it had a denser atmosphere, was warmer, and featured stable bodies of water. The traces of ancient river channels, deltas, and lake deposits discovered on its surface confirm that water existed in a liquid state, not transiently, but over significant geological epochs. These conditions would have allowed for the formation of stable ecosystems, at least at a microscopic level. At some point, the planet lost a substantial portion of its atmosphere, along with its capacity to retain heat and surface liquid water. The primary cause attributed to this is the weakness of Mars's magnetic field. Unlike Earth, with its active core and powerful magnetic field that shields the atmosphere from the solar wind, Mars lost its internal geodynamics early in its history. Consequently, charged particles from the Sun gradually eroded the atmosphere into space. This process occurred slowly but relentlessly. As atmospheric density dropped below a critical threshold, the greenhouse effect weakened, temperatures fell, and water first froze and then partially sublimated into the vacuum of space. The loss of its atmosphere rendered the planet vulnerable to radiation, resulting in a dry and unstable climate. It is precisely this early period of Martian history that is considered the most promising for the potential existence of life. With the presence of water, energy sources, and basic chemical elements, the conditions for the emergence of simple organisms would have been present. If life did indeed originate on Mars during its more clement epochs, when water flowed across its surface, it may have retreated to subsurface environments as conditions deteriorated. Subsurface habitats would have provided relative temperature stability and protection from radiation, especially after the loss of the atmospheric shield. It is in these sheltered zones, shielded from external influences, that microorganisms capable of subsisting on chemical reactions within rocks or near potential underground heat sources might have persisted. Current missions are specifically focused on investigating such regions. Since March of 2020, the Perseverance rover has been active on the Martian surface. It is exploring Jezero Crater, which once held a lake fed by a river system in ancient times. This location was chosen deliberately. Deposits formed in a delta are capable of preserving organic molecules and microscopic structures for billions of years. Perseverance not only studies the region's geology, but also collects samples of Martian soil and rock into sealed containers, intended for eventual return to Earth. The sample return project is scheduled for the 1930s. Its objective is to conduct laboratory analyses of Martian materials on Earth for the first time, utilizing all contemporary methods of organic and isotopic chemistry. This approach will allow for a highly accurate determination of whether the samples contain evidence of ancient biological activity. In addition to NASA's mission, China also dispatched the Tianwen-1 mission to Mars. This marked China's first comprehensive interplanetary endeavor, encompassing an orbiter, a lander, and a rover. Since May of 2021, China's Zhurong rover has been operating in the Utopia Planitia region. It is investigating geological features, conducting spectral analyses of the soil, and capturing images of the surrounding landscape. Although this mission does not involve sample return, it also aims to refine our understanding of past conditions and expand mapping data. Currently, scientific attention is concentrated on two key areas: the search for residual traces of ancient life and the assessment of its potential for preservation in subsurface zones. Both avenues are united by the pursuit of an answer to a fundamental question. Could Mars in its youth have been a planet where life began to evolve in parallel with Earth? Investigations are ongoing, and each new sample, measurement, or surface image brings us closer to a more precise understanding of this ancient world. While Mars is considered a cold, arid planet with evidence of lost warmth, Venus presents an entirely contrasting environment, virtually enveloped in heat and pressure. Contemporary Venus is one of the most inhospitable planets in the solar system. Surface temperatures reach as high as 460 degrees Celsius, sufficient to melt lead. The atmospheric pressure is approximately 90 times greater than Earth's, equivalent to the pressure found 1 kilometer beneath the ocean's surface. To exacerbate matters, the planet's atmosphere is permeated by dense clouds laden with sulfuric acid, obscuring the surface from visible light and generating a potent greenhouse effect. This depiction of Venus is hardly conducive to notions of life. However, research from recent decades has gradually reshaped our understanding of its past. Based on climate models developed with NASA specialists, there is a possibility that between 2 and 3 billion years ago, Venus may have been quite different. It is hypothesized that during those eras, oceans of liquid water existed on its surface, and its temperature and atmospheric composition were far more benign, approaching Earth-like conditions. The planet's climate was maintained by a cloud cover that reflected solar radiation and a stable water cycle that may have persisted for hundreds of millions of years. Under such parameters, Venus could have been potentially habitable, at least until a runaway greenhouse effect triggered a catastrophic thermal collapse. The reasons for this transformation are not fully understood. It is believed that the evaporation of oceans and the accumulation of carbon dioxide in the atmosphere led to an uncontrollable intensification of the greenhouse effect. This resulted in a cascading increase in temperature and the complete evaporation of water. One of the primary arguments supporting the notion that Venus once possessed a significant volume of water is the ratio of heavy hydrogen, or deuterium, to regular hydrogen. On Venus, this ratio is tens of times higher than on Earth. This suggests that the lighter hydrogen from water molecules evaporated into space, while the heavier deuterium remained. Following the dissociation of water molecules, hydrogen was carried away by the solar wind, as the planet lacks an effective magnetic field. Due to its exceptionally slow rotation, Venus's magnetic field is approximately 100,000 times weaker than Earth's and is incapable of protecting its atmosphere from the impact of the solar wind. Oxygen released during these processes did not accumulate in the atmosphere, but most likely reacted with rocks and sulfur compounds, or to a lesser extent, also escaped the atmosphere. The outcome of this process is a dense, arid atmosphere, saturated with carbon dioxide, featuring acidic clouds and the complete absence of any hydrosphere. These transformations rendered Venus's surface utterly hostile to any known form of life. However, not all attention is focused on the surface. In 2020, a research team claimed the detection of phosphine gas in Venus's atmosphere, a substance typically associated with biological processes on Earth. Phosphine can be a byproduct of anaerobic microbial metabolism. Its detection ignited a vigorous scientific debate, although the data was subsequently called into question and the measurement methodology revised. The mere fact of the discussion opened a new avenue of research. Some scientists do not rule out the possibility that stable zones might exist in the upper atmospheric layers, where temperatures and pressures are significantly lower than at the surface, potentially supporting life adapted to an acidic environment. Microorganisms, if they exist, could be sustained within aerosol droplets, deriving sustenance from substances present in the planet's gaseous envelope. To obtain more precise data on Venus's past and assess the likelihood of its habitability in early geological epochs, new research missions are planned. These include Da Vinci and Veritas. The former will focus on studying the atmospheric chemical composition and will conduct a descent scan en route to the surface. This will help refine the evolution of the greenhouse effect and identify potential remnants of water vapor and favorable conditions in the past. The latter mission will concentrate on the planet's geological structure. Utilizing radar mapping, it will aid in understanding the tectonic and volcanic processes that may have played a crucial role in the climate catastrophe. Modern Venus remains a world of extremes, but its past and the potential traces of habitability make it one of the most important subjects in studying planetary climate change and the potential fate of Earth-like worlds. After discussing the planets closest to us, it is time to examine worlds significantly farther from the Sun. We journey to the outer regions of the solar system, to the gas giants, Jupiter and Saturn. Their moons, at first glance, appear cold and lifeless, covered in ice and devoid of atmosphere. However, beneath these frozen shells lie entire oceans. Liquid water is preserved there due to internal heating generated by tidal friction. It is precisely these worlds, unseen by the naked eye and removed from light, that may prove promising for the existence of primitive life. The focus is on Jupiter's moon, Europa, and Saturn's moon, Enceladus. Among Jupiter's moons, Europa is considered one of the most probable candidates for harboring life. Despite its diameter being smaller than that of our moon, a colossal subsurface ocean, whose volume exceeds that of all Earth's seas combined, lies beneath its icy crust. The thickness of the ice layer varies from 10 to 30 kilometers. Below this lies a layer of liquid water, estimated to be up to 100 kilometers deep. This aquatic world does not freeze due to tidal friction, arising from Jupiter's gravitational influence, which compresses and stretches the moon's interior, converting mechanical energy into heat. Europa's surface is crisscrossed by a network of fissures and lines, forming intricate, almost geometric patterns. These features indicate the mobility of the ice and its contact with the liquid water below. In many areas, so-called chaotic terrains are observed, regions where the ice appears to have been fractured, crumpled, and mixed. These could be locations where the subsurface ocean erodes the crust from below, pushing fragments to the surface. Such areas are of particular interest, as they may preserve a chemical link between the ocean and the surface environment. In the late 1990s, the Galileo spacecraft, exploring Jupiter's system, provided crucial data. It detected induced magnetic perturbations, indicating the presence of an electrically conductive fluid layer, most likely saline water. Additionally, spectroscopic data was obtained, suggesting the presence of salts and sulfur-containing compounds on the ice surface. These substances were likely ejected from the ocean through cracks in the crust. Although Galileo did not detect organic traces, the very possibility of chemical exchange between the ocean and the surface makes Europa extremely compelling for further biomarker searches. Beneath Europa's surface, at the bottom of its hidden ocean, hydrothermal vents analogous to those found in Earth's oceans could very well exist. Such vents are formed by the interaction of water with heated rocks and serve as the foundation for entire ecosystems independent of sunlight. On Earth, in similar conditions, bacteria and archaea thrive, utilizing chemosynthesis, the conversion of chemical energy into organic matter. These organisms form stable communities that sustain food chains in complete darkness. It is precisely these conditions that, at least theoretically, could support life in Europa's ocean. To test these hypotheses, the Europa Clipper mission is being developed and is slated for launch in the near future. The spacecraft is expected to arrive in Jupiter's system in the early 1930s and will conduct dozens of low-altitude flybys over Europa's surface. It will be equipped with spectrometers, radar, and particle analyzers capable of detecting biomarkers and analyzing the ice structure. Particular attention will be paid to areas where recent ejections of material from the ocean are likely. If organic molecules or unusual isotopic ratios are found on the surface, it would provide a strong argument for the existence of life beneath. While Europa requires penetrating kilometers of ice, Enceladus, Saturn's moon, actively ejects samples of its internal ocean into outer space. This is one of the most astonishing objects ever studied in the solar system. Its diameter is approximately 500 kilometers, but even at this modest size, it exhibits phenomenal activity. In the region of the South Pole, powerful geysers have been discovered, expelling jets of water, vapor, salts, methane, ammonia, and microscopic ice particles into space. These jets erupt from fissures in the icy crust, known as tiger stripes. Observations made by the Cassini spacecraft over 13 years have shown that the ejecta contain organic compounds, including complex carbon-based molecules. It was also revealed that the composition of these geysers indicates contact between water and a rocky seafloor, a necessary condition for chemical reactions, similar to those that sustain microbes on Earth. Such processes include, for instance, the reaction between water and minerals, which releases hydrogen and methane. These substances could serve as an energy source for microorganisms analogous to Earth's methanogens. On Earth, methanogenesis is considered one of the oldest metabolic pathways, and its presence on Enceladus, coupled with other substances, makes the hypothesis of life's existence highly realistic. Scientists emphasize that even if the methane is not produced biologically, the conditions under which it arises still represent a favorable environment for a potential biosphere. Various options for returning to Enceladus are currently being discussed. One of these is the Life Finder project. This mission would involve flying through the geyser plumes, collecting samples directly from the jets, and analyzing them for complex organic molecules, proteins, or other potential signs of life. This approach bypasses the need for a landing on the icy surface and provides immediate access to material directly originating from the ocean. While the exact implementation date has not yet been determined, this concept is considered one of the most promising for astrobiology in the coming decades. Another astonishing moon of Saturn that sparks intense scientific interest is Titan. It is the planet's largest moon and even surpasses Mercury in size. Unlike other moons in the solar system, Titan possesses a dense atmosphere, so dense that the pressure on its surface is approximately 1.5 times that of Earth's. It is the only place beyond Earth where liquid is consistently present on its surface, not water, but methane and ethane. Titan experiences rain, and rivers, lakes, and even coastal shorelines form, all composed of hydrocarbons. This setting creates unique conditions. Titan became the first celestial body on which a complete liquid cycle, analogous to Earth's, was discovered. Only instead of water, light organic compounds are involved. The moon is enveloped in a thick layer of orange haze, and in its upper atmosphere, under the influence of solar radiation and particles from Saturn's magnetosphere, complex photochemistry occurs. As a result, a diverse array of organic compounds are formed, including nitriles, hydrocarbons, and polycyclic aromatic molecules, which then settle on the surface. This is a sort of prebiotic laboratory where chemical reactions akin to those that might have initiated life on early Earth could take place. A deep understanding of these processes became possible thanks to the Cassini-Huygens mission. In 2005, the Huygens probe successfully landed on Titan's surface. It was the first mission in history to reach such a distant and dense world. It transmitted images of plains dotted with rounded pebbles of ice, along with data on the atmospheric composition and the uppermost soil layer. The instrumentation detected organic substances deposited from the atmosphere, including complex molecules associated with carbon chemistry. These are not biological organisms, but they demonstrate that the chemical raw materials necessary for life are abundant here. Titan's distinctive feature is that alternative forms of life, based on liquid methane rather than water, could potentially exist here. Surface temperatures are around minus 180 degrees Celsius, and water here is as hard as rock. However, methane remains in a liquid state under these conditions, serving as a solvent. While Earth's biosphere thrives on water as its universal solvent for biochemical processes, the moon Titan presents a compelling possibility for life with an entirely different molecular architecture, potentially utilizing methane-based reactions and existing in extreme cold. Though these theoretical frameworks lack empirical substantiation currently, they are actively being explored at the intersection of astrobiology, chemistry, and theoretical biophysics. To gain deeper insights into the enigmatic nature of this world, NASA is preparing an ambitious new mission, Dragonfly. Its projected launch is slated for the year 2027, with arrival at Titan anticipated in 2034. Diverging from all prior exploratory endeavors, Dragonfly will not function as an orbital satellite or a surface rover. Instead, it is conceived as an aerial drone, engineered for extensive flight across the lunar landscape. Titan stands as the sole celestial body within our solar system, whose unique combination of a dense atmosphere and low gravitational pull makes such a flying platform feasible. The Dragonfly spacecraft will possess the capability to land, ascend, and traverse from one area of scientific interest to another, meticulously investigating diverse geological and chemical environments. The primary objectives of this mission encompass the detailed analysis of organic compounds, thorough examination of the moon's surface features, the search for indications of past or dormant life, and the identification of conditions conducive to the abiotic synthesis of complex organic molecules. Dragonfly is poised to represent the inaugural attempt in history at performing mobile astrobiological reconnaissance within the atmosphere and upon the surface of an extraterrestrial world. Should Titan indeed hold the keys to understanding alternative life forms, this mission could mark one of the most pivotal milestones in the annals of space exploration. Our current astronomical capabilities allow for the detection of several hundred to over 1,000 new planets, depending on the sensitivity of our instruments and the thoroughness of our surveys. The methodologies for exoplanet detection are advancing year by year. One of the most reliable techniques is the transit method. This approach relies on observing a slight regular dip in a star's brightness when a planet passes in front of its stellar disk, thereby obscuring a portion of its light. It was precisely this method that the renowned Kepler telescope employed, which provided a significant impetus for discovering thousands of new planets. This technique is particularly advantageous for large-scale surveys, as it enables continuous monitoring of a vast number of stars simultaneously. Another established approach is the radial velocity method, also known as the Doppler method. This technique detects stellar wobbles caused by the gravitational pull of a planet orbiting the star. Even if the planet itself remains unseen, we can observe the subtle motion of the star as it slightly shifts towards and away from us. This method not only confirms the existence of a planet, but also allows for the measurement of its mass. Additional methods are also in use, including direct observation, where powerful telescopes can capture the infrared glow emitted by an exoplanet against the backdrop of its star. This is achievable only in exceptional circumstances, specifically for very massive, young and hot gas giants that are situated far from their host star and radiate intensely in the infrared spectrum. The intrinsic luminosity of stars is tens of millions of times greater than the reflected light from their planets, necessitating sophisticated equipment and techniques to suppress stellar glare. Despite these challenges, actual images of several such exoplanets have been obtained, including those within the HR 879 system, where the movement of 4 planets was successfully tracked. While these images do not reveal surface details, they offer direct visual confirmation of a planet's presence as a luminous point adjacent to its star. This represents a significant advancement in contemporary astronomy, paving the way for the study of planetary systems in their dynamic interactions. In recent years, the James Webb Space Telescope has played a crucial role in exoplanet observation, possessing the capability to analyze the spectrum of light that traverses a distant planet's atmosphere during a transit. Through this telescope, scientists seek to identify traces of water vapor, methane, carbon dioxide, ozone, and other potential biomarkers within the atmospheres of these distant worlds. Such measurements demand the utmost precision and can sometimes take months to complete, yet they offer the potential not merely to confirm a planet's existence, but also to ascertain the degree to which it truly resembles Earth. The discovery of exoplanets has provided humanity with a fresh perspective on our galaxy. What was once considered an anomaly, a planet with liquid water and habitable conditions, is now increasingly viewed as a potentially recurrent cosmic narrative. The question of how many of these worlds are genuinely capable of sustaining life remains unanswered. However, the more we learn, the less unique Earth appears to be. Among the vast multitude of exoplanets we have discussed, particular attention is drawn to those situated towards the higher end of the Earth Similarity Index scale. As previously established, this index takes into account parameters such as mass, radius, and temperature, comparing a planet to the conditions present on our own Earth. Values approaching unity indicate a high degree of external resemblance, although they do not, in themselves, guarantee habitability. Nevertheless, they serve to identify the most compelling targets for subsequent observation. One such world is Kepler 438b. This planet was detected by the Kepler telescope and immediately captured the attention of astronomers. Its similarity index stands at approximately 0.88, positioning it as one of the most Earth-like exoplanets discovered to date. It belongs to the super-Earth category, comprising rocky planets whose size and mass slightly exceed those of Earth. The radius of Kepler 438b is approximately 12% larger than Earth's, and its mass is estimated to be between 1 and 2 Earth masses, although the precise figure remains undetermined due to the inability to measure it directly thus far. The planet orbits the star Kepler 438, situated approximately 470 light-years away from us in the constellation Lyra. This star is classified as a red dwarf, meaning it is a cool and low-mass star. Its mass is roughly half that of our Sun, and its luminosity is merely a few percent of the Sun's. Consequently, the habitable zone around it is located much closer to the star than in our own solar system. Kepler 438b completes a full orbit around its star in 35 Earth days, placing it within the presumed zone where liquid water could exist on its surface. However, this system presents significant characteristics that cast doubt on the planet's potential suitability for life. Like many stars of its class, Kepler 438 is an exceptionally active red dwarf. Observations have revealed that it frequently emits powerful flares or bursts of radiation, which can be tens or even hundreds of times more intense than the strongest solar storms. In recent years, it has been recorded that the star emits such flares approximately once every 20 days on average. Furthermore, the energy from some of these flares has been sufficient to cause significant ionizing radiation exposure to nearby planets. At this level of stellar activity, the planet's atmosphere, even if it initially existed, could have undergone severe erosive processes. In the absence of a protective magnetic field, the atmosphere can gradually be stripped away by streams of charged particles. If the planet lacks its own magnetic shield, akin to Earth's, this could imply that its surface is bombarded with radiation, and any conditions conducive to a stable biosphere are obliterated. Conversely, if a magnetosphere is present, it could potentially shield the atmosphere and render the planet more stable. However, this hypothesis remains speculative. We do not possess definitive knowledge regarding the presence or absence of a magnetic field on this planet. It is also noteworthy that orbital parameters suggest a high probability of tidal locking. This means one hemisphere of the planet might perpetually face the star, while the other remains in eternal shadow. Under such conditions, a thermal imbalance between the hemispheres is plausible, but a dense atmosphere, if present, could mitigate this contrast by facilitating heat transfer. It remains unknown whether Kepler 438b possesses an atmosphere, what its composition might be, or if it hosts any moons. Such data can only be obtained by more precise instrumentation in future missions, such as next-generation telescopes capable of performing transit light spectroscopy. For now, the planet remains theoretically one of the most promising candidates, albeit with a crucial caveat. A high degree of similarity does not equate to high habitability. Kepler 438b serves as an example of how a confluence of encouraging parameters and a harsh stellar environment creates a complex scenario. Such planets expand our understanding of the diverse conditions under which life might exist, and compel us to reconsider the role of stars in the destiny of potentially habitable worlds. We now shift our focus to a different stellar system, located approximately 40 light-years from Earth. This is the TRAPPIST-1 system, which hosts several rocky planets and has long been a focal point of astronomical interest. The appeal of this system stems not only from its proximity, but also from its uniquely compact configuration. 7 exoplanets orbit the star, and at least 3 of them reside within the presumed habitable zone. One of these is TRAPPIST-1e. It ranks among exoplanets with a high Earth similarity index, approximately 5, placing it among the most compelling targets for astrobiological research. Its mass is estimated at around 70% of Earth's, and its radius is approximately 90% of Earth's. In terms of density, the planet closely matches Earth, suggesting a predominantly rocky composition with a metallic core. The planet is situated within its star's habitable zone, where temperatures could potentially allow for the existence of liquid water on its surface. It completes a full revolution around its star in 6 Earth days, indicating an extremely close orbital distance. Notably, the entire TRAPPIST-1 system is so compact that the orbits of all 7 planets fit within the orbit of Mercury. This creates a rich dynamical environment with resonances and gravitational interactions between the planets, which aid in precisely determining their masses and densities. The star TRAPPIST. One itself is an ultra-cool red dwarf with a surface temperature of approximately 2,500 degrees Celsius. It possesses a mass that is 10 times smaller than the Sun's and emits only a fraction of a percent of the Sun's light. The majority of its radiation is emitted in the infrared spectrum, meaning the energy received by the planet is distributed differently than on Earth. However, the overall thermal load corresponds to conditions that could permit liquid water, provided an atmosphere is present. TRAPPIST-1e is highly likely to be tidally locked, with one side perpetually facing the star and the other eternally shrouded in darkness. Despite this, climatic models suggest that with a sufficiently dense atmosphere, the temperature differential could be smoothed out through efficient heat transfer. This makes the existence of a stable band of temperate climate possible along the terminator, the boundary between light and shadow. Information regarding the planet's atmosphere is currently limited. Preliminary observations using the James Webb Space Telescope have not detected evidence of a dense water envelope on this planet, unlike some of its neighbors. This reduces the likelihood of runaway greenhouse heating and makes it an even more intriguing candidate. The hypothesis of an atmosphere composed primarily of nitrogen, with additions of carbon dioxide or other inert gases, remains plausible. If TRAPPIST-1 indeed possesses a stable atmosphere and liquid water exists on its surface, even partially, the question arises: what forms of life could potentially emerge in such unusual conditions? The planet receives primarily infrared radiation. Therefore, if a biosphere utilizes photosynthesis, it would likely be based on pigments sensitive to long wavelength light. Such organisms could hypothetically exhibit dark coloration, black, purple, or reddish brown, enabling them to capture maximum available energy. The gravitational pull on TRAPPIST-1e is slightly lower than Earth's, suggesting that potential life, particularly multicellular organisms, might be more elongated and less dense. If the climate is stable and atmospheric pressure is not excessively high, developed terrestrial ecosystems adapted to dim illumination and high humidity could exist. On the sunlit side, organisms resilient to constant radiation and capable of energy storage might dominate, while on the dark side, creatures relying on chemosynthesis, internal heat, or residual infrared radiation could thrive. The skin color of living beings would likely depend on local conditions. On the illuminated side, it would probably be dark to maximize light absorption. Conversely, on the shadowed side, it might be pale or translucent if the inhabitants utilize bioluminescence or infrared vision. Such asymmetry could even exist within a single organism if it inhabits the transitional zone between light and darkness. TRAPPIST. One remains one of the most extensively studied and promising exoplanets. Combined with its proximity to Earth, stellar stability, rocky composition, and potential atmosphere, it represents a primary target for astrobiological investigations. Among exoplanets that superficially resemble Earth but are located considerably farther away, Kepler 452b stands out. This planet has earned the informal moniker Earth's older sister due to its similar parameters and its orbit around a star positioned at a comparable distance to our own. However, its stellar system is significantly older, and the planet itself is larger, more massive, and older than our Earth. The planet orbits the star Kepler 452, which is located approximately 1,400 light-years from Earth in the direction of the constellation Cygnus. The star belongs to the same spectral class as our Sun, but is approximately 10% brighter and 500 million years older. This makes it a crucial object for studying the evolution of planetary systems, analogous to our own, but in a more advanced stage of development. The planet itself is a super-Earth, calculated to be 60% larger in radius than our planet. Its precise mass has not been directly measured, but based on its assumed density, it could be 5 times heavier. Such parameters suggest a high probability of a rocky structure, although the possibility of a more massive atmosphere or the presence of water ice in the mantle cannot be entirely ruled out. The Earth Similarity Index for Kepler 452b is approximately 0.83, making it one of the most Earth-like among discovered objects at greater distances. The planet is situated within the habitable zone, orbiting at a distance comparable to Earth's, with its year lasting approximately 385 days. Such orbital stability, coupled with the star's moderate radiation output, creates favorable thermal conditions. Surface temperatures on the planet could be similar to Earth's, provided it possesses a dense atmosphere and a developed greenhouse effect. However, the age of the system plays a dual role. On one hand, over more than 6 billion years, stable geological and climatic processes could have evolved on the planet. On the other hand, the prolonged influence of stellar radiation, particularly in its early stages, could have led to atmospheric loss, especially if the planet lacked a magnetic field or sufficient gravitational mass to retain it. Consequently, the question of the planet's habitability remains open. Another factor complicating its study is its considerable distance. The planet is much farther away than, for instance, TRAPPIST1, making it impossible to study with the same level of detail. Current telescopes do not permit atmospheric analysis or confirmation of surface composition. Nevertheless, the very existence of such an object, with conditions so similar to Earth's and situated in a mature orbit, suggests that Earth-like planets may be a common phenomenon around yellow dwarfs similar to our Sun. If Kepler 452b indeed possessed a stable atmosphere and liquid water, life on it would likely have evolved under conditions of increased pressure and greater gravity compared to Earth. Surface organisms might be more compact and robust, adapted to higher gravitational pull and potential temperature fluctuations. The more mature age of the system allows for the possibility that if life did emerge there, it could have progressed through complex evolutionary stages. This planet marked a significant milestone in the quest for extraterrestrial life. It was the first discovered object of terrestrial type, orbiting a sun-like star within the habitable zone. Although it is too distant for immediate missions and investigations, it played a pivotal role in the realization that our planet is not unique in its characteristics. Similar worlds may be scattered throughout the galaxy. Once an exoplanet is detected, the subsequent crucial task becomes the study of its atmosphere. It is within the gaseous envelope that the most vital information may be concealed, such as the presence of water vapor, oxygen, methane, ozone, and other molecules capable of indicating biological or geochemical processes. These components, particularly in characteristic combinations, are considered potential biomarkers, indicators that may point to the presence of life. Since exoplanets are too small and distant to be observed directly, scientists employ transit spectroscopy. This method is based on observing how starlight passes through a planet's atmosphere when it crosses the star's disk. As the planet transits in front of its star, a portion of the light is filtered by its atmosphere, and different gases absorb light at specific wavelengths. This creates a spectroscopic fingerprint that reveals the atmospheric composition. This process requires highly sensitive telescopes capable of detecting minute changes in the radiation flux. One of the primary instruments for this purpose is the James Webb Space Telescope, launched in late 2021. It operates in the infrared spectrum, which is ideal for analyzing cool stars and planets. In its initial years of operation, the telescope has already begun acquiring atmospheric spectra of some exoplanets, predominantly gas giants so far, but the method itself is being successfully refined and progressively applied to smaller, rocky worlds. Among its early achievements are the detection of water vapor, carbon dioxide, hydrogen sulfide, and methane in the atmospheres of hot exoplanets. While these are not yet definitive signs of life, they confirm that the technology is functional and allows for the analysis of chemical composition with increasing accuracy. Prospectively, with continued data accumulation, it may become possible to infer temperatures, pressures, cloud structures, and even potential climatic circulation patterns on a planet's surface. However, the method has significant limitations. Firstly, it is applicable only to planets that transit their star's disk from our observational perspective. Only a small fraction of known systems exhibit this alignment. Secondly, the signal itself is exceedingly weak. Even under ideal conditions, the light passing through an exoplanet's atmosphere constitutes a mere fraction of a percent of the total flux. If the star is active, as is common with red dwarfs, flares, magnetic storms, and sunspots, can distort or mask the signal, hindering analysis. Additional complexities arise from distance. The farther a system is, the weaker the signal becomes, and the more time is required for observations. Even with extended exposures, the data remains noisy and necessitates complex computer processing. Furthermore, current telescopes lack the precision to thoroughly investigate the tenuous atmospheres of Earth-like planets, especially those orbiting bright yellow or white stars whose luminosity far surpasses the faint signal from the planet. Despite these challenges, progress in spectroscopy continues. New methods are being developed, including direct spectral separation of planet and starlight, as well as coronagraphs and star shades designed to suppress starlight and study the planet in isolation. Next-generation telescopes such as LUVOIR and HabEx are planned for deployment in the coming decades. These instruments will be capable of performing detailed atmospheric analyses of Earth-like planets, even those situated at significant distances. The question of the existence of other intelligent civilizations remains one of the most captivating and fundamental for contemporary science. If life, particularly microscopic life, can be a widespread phenomenon in the universe, then the emergence of intelligence is a far more complex and rare process. It is precisely for this reason that specialized programs have been developed, focusing not on detecting biological traces, but on identifying evidence of technological activity. The largest and most renowned initiative of this kind is the SETI project, or the Search for Extraterrestrial Intelligence. The network's program focuses on detecting narrowband radio signals, meaning those not produced by natural phenomena. In nature, most objects emit across a broad spectrum of frequencies. whereas artificial signals, such as radio or television, are confined to a very limited bandwidth. Discovering such a signal from space with a distinct frequency structure could serve as evidence for the existence of a technological civilization. For these purposes, radio telescopes are employed, capable of capturing the faintest fluctuations within the radio spectrum. One of the conventional frequency ranges for this search is approximately 1.420 megahertz, corresponding to the emission frequency of hydrogen atoms. This selection is deliberate, as hydrogen is the most abundant element in the universe, and an intelligent civilization might leverage its ubiquity as a basis for signal transmission. The most notable event in the network's observational history remains the so-called WOW signal, recorded in 1977. It was detected by radio astronomer Jerry Ehman using the Big Ear radio telescope. During a routine sky survey, the telescope registered a narrowband radio signal lasting 72 seconds, precisely the duration permitted by the antenna configuration for observing a particular patch of sky. The signal was so strong and clear that Ehman, impressed by what he saw on the printout, wrote "Wow" in the margin, giving it its name. The signal exhibited all the hallmarks of artificial origin. It fell within the expected frequency range, possessed an appropriate waveform, maintained a stable frequency, and ceased abruptly upon exiting the receiving zone. However, despite numerous subsequent attempts to reacquire it, the results were negative. It remains an isolated incident without repeated confirmation. Neither natural sources nor terrestrial interference could be definitively identified as its cause. In recent years, a hypothesis has been proposed suggesting the signal might have stemmed from an astrophysical event, such as a stellar flare or a magnetar colliding with a cloud of cold hydrogen. Such a combination could amplify radiation at the hydrogen line frequency, generating a burst with parameters similar to this signal. Nevertheless, this theory has not yet received definitive validation, and the signal continues to be one of the most enigmatic episodes in the network's history. The history of observations also includes more mundane occurrences. For instance, for many years, the Parkes Observatory in Australia detected peculiar pulses that remained unexplained for a considerable time. It was later discovered that these signals appeared whenever observatory staff opened the door of a microwave oven located near the antenna. The pulse generated during this action would enter the telescope's reception range and be registered as a potential anomalous signal. This incident became a classic example of how even common household appliances can trigger false alarms in radio astronomy observations. Nevertheless, the observations persist. Increasingly sensitive receivers, automated algorithms, artificial intelligence, and supercomputer data processing are being utilized. New telescopes and antennas are expanding their coverage to encompass a greater number of stars and frequency bands. The network has long since transcended the scope of individual telescopes, evolving into a distributed observational system involving institutions worldwide. In 2015, the most ambitious project to date for the search for extraterrestrial intelligence breakthrough, Listen commenced. It was initiated under the Breakthrough Initiatives program and received financial backing of $100 million over a 10-year period. The project's primary objective is to systematically scan 1 million nearby stars and several hundred nearby galaxies for artificial radio signals, optical pulses, and other potential indicators of technological activity. Observations have been and continue to be conducted using major radio telescopes, including the Green Bank Observatory in America and the Parkes Observatory in Australia. The project's equipment allows for the simultaneous tracking of millions of frequency channels, covering a broad spectrum of the radio range with high precision. In addition to radio observations, the project also encompasses the search for laser pulses in the optical spectrum, which could serve as an alternative form of interstellar communication. One of the key features of Breakthrough Listen has been the utilization of artificial intelligence for analyzing the colossal volume of data. Machine learning algorithms help filter radio interference, detect anomalous signals, and identify statistical deviations from background radiation. Through this approach, over 2.5 million observational sessions have been analyzed within the project. Although the project has not yet recorded a confirmed signal from an extraterrestrial civilization, it has uncovered some unusual signals during its course that have garnered interest from the scientific community. One of the most discussed cases is a signal, provisionally designated as BLC1. It was detected in 2019 in the direction of Proxima Centauri, the closest star to our Sun. The signal was narrowband stable and did not coincide with known terrestrial radio interference sources. Initially, it generated significant interest as it originated from a patch of sky containing an exoplanet with potentially habitable conditions. However, further analysis revealed that the signal's source was likely anthropogenic, meaning it was connected to human activity. Researchers concluded that it was most likely a complex combination of terrestrial radio signal interference that coincided in time and purity with the observation direction. Nevertheless, the very need for such rigorous verification underscored the importance of employing automated and critically oriented approaches in data processing. Besides BLC1, Breakthrough Listen periodically registers individual signals that lack an obvious explanation but are not repeatable, thus precluding reliable verification. These instances serve as reminders of the challenges involved in the search. A signal could be genuine but transient, or it might arise from a confluence of poorly understood technical factors, creating the illusion of an anomaly. Breakthrough Listen is not merely an attempt to intercept an extraterrestrial radio transmission. It is a systematic, large-scale, and technologically advanced program that lays the groundwork for future endeavors, improves radio observational methods, standardizes analysis algorithms, and trains a new generation of researchers. Even if no signal from extraterrestrial intelligence is ever detected, this work is already expanding the technical and theoretical horizons of radio astronomy. While the majority of projects concentrate on the search for radio signals, another avenue exists, attempting to find indirect traces of technological activity not related to message transmission. This idea is based on the assumption that a highly advanced civilization, possessing considerable resources and time, might leave behind discernible technical structures or energy footprints detectable across interstellar distances. Such approaches are collectively known as the search for technosignatures. One of the most well-known hypotheses in this field remains the concept of a Dyson sphere, or megastructure, hypothetically constructed around a star to capture its radiation entirely. The idea was proposed by physicist Freeman Dyson, who suggested that an advanced civilization might utilize stellar energy far more efficiently than humanity does. A complete shell, or array of solar panels, encircling a star would absorb most of its radiation and re-emit it in the infrared. Consequently, one method of detecting such a structure is by searching for thermal anomalies, where a star emits less visible light than expected, but radiates an excess of infrared. Within the framework of analyzing such objects, studies have been conducted on stars exhibiting unusual behavior. The most famous example is Tabby's star. Observations indicated that its brightness irregularly decreased by up to 20% with an inexplicable periodicity. This sparked intense discussions, including the hypothesis of the star being partially obscured by a megastructure. It later became apparent that such eclipses were likely caused by dust clouds or large comets, but the incident itself served as a starting point for the systematic search for similar anomalies. Another direction involves analyzing optical signals. If radio transmissions are an energy-efficient means of communication over vast distances, then laser pulses could be a way to create brief, yet bright and distinct signals visible across interstellar distances. Modern ground-based telescopes can detect nanosecond laser flashes, provided they are repeatable or sufficiently bright. Under the Breakthrough Initiatives program, efforts are already underway for the systematic monitoring of nearby stars in the optical spectrum to search for such pulses. To cope with the enormous volumes of observational data, astronomers are actively implementing artificial intelligence and machine learning. Modern algorithms can process billions of signals, identify deviations from statistical norms, filter out false positives, and highlight anomalies that might be imperceptible to humans. Such systems are already in use in projects like Breakthrough Listen, and their role is expected to grow in the coming years. Despite extensive observations and efforts in signal detection, no reliable evidence for the existence of intelligent extraterrestrial civilizations has been obtained to date. This discrepancy between the high theoretical probability of life in the universe and the complete absence of any data constitutes the essence of the so-called Fermi paradox. Its core, formulated in the mid-20th century, is simple. If intelligent life forms are widespread, why have we not yet detected their signals or any traces of their presence? According to preliminary estimates, our Milky Way galaxy alone may host over 100 billion stars, and a significant portion of these possess planetary systems. If even a small fraction of these planets are within the habitable zone, and if life develops on just one out of thousands of those, then statistical reasoning suggests that intelligent life should have emerged multiple times in various locations. However, all searches for both radio signals and technological traces have thus far yielded no positive results. One possible explanation for the paradox is the hypothesis that intelligent life itself is extremely rare, while microbial life might arise given water and energy. Further development to the level of intelligence requires a series of complex evolutionary transitions, such as the emergence of multicellularity, sexual reproduction, nervous systems, language, culture, and technological thinking. Each of these stages could be so improbable that on a galactic scale, humanity represents a singular exception. In this scenario, we might indeed be alone, simply because analogous processes either never initiated or reached a dead end. There is also a model suggesting that civilizations deliberately avoid announcing their presence. This idea is known as the dark forest hypothesis. It posits that intelligent species are aware of the risks of contact with external forces and prefer complete radio silence to avoid threats. Analogous to a hunter in a dense forest, each entity tries to remain quiet and unnoticed, as any manifestation could lead to demise. In this case, there might be many intelligent inhabitants of the galaxy, but they are all actively concealing themselves. We, as latecomers to this forest, simply haven't yet understood how dangerous it can be to speak loudly. Another popular explanation is that the technological phase of civilization's existence is very brief. Technological advancement inevitably leads to the creation of tools capable of destroying those who use them. This could manifest as global warfare, ecological collapse, biosphere destruction, loss of social stability, or uncontrolled artificial intelligence. In such a model, civilizations self-destruct before achieving the capacity for interstellar travel or contact. Even if such civilizations emerged in the past, they might have vanished long before we began exploring the sky. There are also other less grim but equally logical possibilities. For instance, the assumption that highly advanced civilizations are simply not interested in contact with us. If another intelligence's technological level surpasses ours by tens of thousands or millions of years, then humanity might be perceived as a biologically primitive and scientifically irrelevant phenomenon, no more than noise in the data. Such an attitude might be akin to a modern human, not interacting with bacteria living in the soil. In this hypothesis, we are neither destroyed nor deliberately ignored, but simply unperceived or considered unworthy of attention. Yet another possible explanation relates to differences in perception and cognition. We might be searching for intelligence based on our own criteria, such as radio signals, structures, and logical traces. However, another civilization might be so alien to our logic that its activities are not perceived by us as artificial. For example, their signals could be too fast, too slow, or utilize information carriers that we do not engage with at all, such as neutrinos, gravitational waves, or modifications of dark matter. In such a scenario, contact might be possible, but it simply passes us by, and we are currently unaware of it. The Fermi paradox not only offers no definitive answers, but also expands the horizons of our thinking. It compels us to reevaluate the criteria for life, development, civilizational sustainability, and our own role within the cosmic context. If credible evidence of life beyond Earth, even in its simplest form, is ever discovered, it will be one of the most significant events in human history. The implications will extend not only to science, but also to culture, philosophy, technology, and our understanding of humanity's very place in the universe. Primarily, science will face the necessity of revising fundamental concepts. Biology, still constructed exclusively on terrestrial examples, will gain a new object of study, possibly with different biochemical foundations, other molecules, metabolic pathways, or evolutionary mechanisms. This will broaden not only theoretical boundaries, but also practical applications, from medicine to bioengineering. Chemistry will also be affected, particularly in the realm of organic compounds. If the existence of alternative biochemistry is proven, for example, based on methane, ammonia, or even substances unknown on Earth, it would challenge the current limits of organic synthesis and the resilience of life. Astronomy, in turn, will acquire new criteria for searching for habitable worlds, updating models of planet, star, and galaxy formation with consideration for life-generating potential. However, perhaps the most profound changes will occur on a cultural and philosophical level. The question of our uniqueness is one of the most ancient in human history. And if it turns out that life is not an exception, but a rule, it will compel a reevaluation of our perception of ourselves, the Earth, and the future of civilization. Religious concepts will also need reconsideration, as the existence of extraterrestrial life does not fit within existing traditional worldviews, either theologically, ethically, or historically. It may be necessary to rethink humanity's place in the cosmos, where it will no longer be the center. The need to create a new language of interaction, both literally and metaphorically, will arise. We will have to answer questions such as, how should contact be conducted, if it is possible? What rules should govern interactions between worlds? How to protect alien life from accidental interference? And how to ensure our own safety? Even the mere anticipation of an answer is already altering our thinking. We begin to look differently at what we possess, at nature, at technology, and at Earth's vulnerability. The search for life beyond our solar system becomes not only a scientific task, but also an ethical challenge, shaping a vision of the future where humanity is not the pinnacle of creation, but a part of a complex, unexplored universe. Thank you for watching the lecture to the end. If you enjoyed it, please subscribe to the channel, give it a like, and share the video with your friends. There are many more fascinating journeys through history, science, and space ahead. Until next time, and may the sky above you always be starry.